Hi, everyone. Welcome to this meetup. Thanks for gathering here tonight. I'm excited to be in Paris. This is the first time I'm speaking about Kafka here. My first time I visited, I was just here on vacation. So today's talk is about, putting Kafka Connect, and Kafka Streams, which are new additions to the Apache Kafka platform, together to build a real-time streaming platform. So this talk is more about putting these ideas in practice and less about exactly how it works underneath the covers. Okay, so the plan for the talk is as follows. I'm going to talk briefly about, this idea of moving to a more stream-oriented architecture. What does it mean to represent your data as streams of events? Why that is practical, or why that is required today. Then, for those of you who are not aware, I will give a quick introduction about Apache Kafka. Then we will move on and talk about the ingest solution in Apache Kafka called Connect, and how you can connect different sources and systems with Kafka. Then, we'll talk about streams, which is when data is inside Kafka, how can you process it? And then some concluding thoughts about how Kafka can, how Kafka has arisen to be sort of this streaming platform, and what does it actually mean in the big picture. Okay, so without further ado, let's get started. First question is really, why streaming? Why even bother sort of thinking about this? Up until now, things worked fine. You collect data in batch at the end of the day or several times a day, and then you process it pretty much at the same speed. But today, I'll argue that this isn't sufficient anymore. First of all, unbounded, unordered, large-scale data sets are increasingly common in day-to-day business, whether it's mobile usage statistics or web logs or data from sensor networks or Internet of Things. Stream data is really everywhere. And there is an increasing push towards computing faster results. And that is why this whole area of streaming has, sort of arisen recently. So, the bold claim I'm going to make here is the insight is that businesses actually operate in real time, not batch. So if you go to a store and you buy something, you don't wait there for a couple of hours for your transaction to complete. You actually do that quickly, and then you get out of there. So data collection, for a long time has, as I mentioned, worked in batch fashion, which is a couple times a day you collect data. And hence, processing has worked in a batch fashion. So really, like data processing or data collection, it really provides like an upper bound on how fast your processing can go. You really can't process any faster than you can collect. But with Kafka becoming sort of a de facto standard, getting utilized in thousands of companies, you can now collect data at a very large scale in real time. So there is a huge opportunity to make use of that data quickly and process results quickly in order to gain competitive advantage. So, first of all, what is an event? What does it even look like? Event is nothing but something that has occurred that is relevant to your business. And this is really, different for different businesses. Now, this example is about, just a product view, possibly on some online retail website. It, an event sort of describes more completely what happened that is relevant in order to process it downstream. So it has, sort of a timestamp about when that event occurred. It has a user ID about the person who visited that website to view that product. It has actually the product ID to identify which product it was, and then, several other fields about maybe information about the product or not. Now, this is an example of a product view for an online retailer, but you can imagine an event could be, different for different businesses. It could be a stock ticker for finance, or it could be a page visit for a company like LinkedIn.com. It is really relevant to basically every business. It is just probably not represented in that fashion for a very long time. More examples of event data are, pings from sensor networks. This is basically an unbounded and unending series of data streams coming from sensor networks. Log files, these are events as well. What we tend to think about when you think about log files are essentially in batch fashion. As a file gets written, once it's done, you can then SCP it over and then process it. But really, files are events as well. As here, the example of event is basically one thing or one line, which basically describes sort of how the Apache web server log or how the Apache web server was accessed in this case. More examples, databases are actually closely related to streams as well. Traditional databases are all about tables full of state, but they don't do such a good job of sort of reacting to streams of events that change that state, right? Basically, tables have no notion of time. Here's an example of a table. It has two rows, key 1 and key 2, and it has a certain value. Now, this is actually, this is exactly what a table represents, is the latest view of things. You actually don't know how that view changed. So if you think about how a table gets created over time, at time 0, it might have a single row. At time 1, you add another row. And at time 2, you just update some row. So if you go one step further and you think about, what those operations are, those are merely like, put operations. And if you view this as a stream of events, then you will realize that this table is actually created from a stream of events. It is just that it is the latest and the greatest view of what that stream means. Now, not every stream looks or feels the same. This is a special stream. It has keys and values where values provide updates for the keys that were mentioned earlier in the stream. Some streams are basically record streams where either they don't have keys or might have keys that are totally unrelated to each other. Okay, so, what are the uses of a stream? The first use of a stream, it is sort of largely used to create a data pipeline, which is instead of, ingesting data in batch, you can now do it in a streaming fashion. And more importantly, the use of a stream is actually to enable stream processing. So a lot of what today you think of things that should happen only in Hadoop or the data warehouse, a lot of those queries can actually be done on top of a stream. So, in some sense, processing is just reacting to streams of events, where as a reaction, you might send it to Hadoop or the warehouse, or as a reaction, you might send it to Elasticsearch to index it further, or as a reaction, you might just process it on the fly and forget about it. So, thinking about how companies actually do this, or how do they used to do this, hopefully. So this is a giant mess that we had at LinkedIn, where over time, due to the lack of Kafka, there were lots and lots of these one-off point-to-point connections. So early on, in the very early days, you start with, one database, and then you have one, Hadoop and data warehouse. And in that view of the world, ingesting data from one place to the other place is actually not a big deal. You write some script, and even though it SCPs, you can SCP it quickly, and it sort of works, right? But then over time, the two big changes that we observed that happened in the last few years is that one, the sources or the variety of sources and the volume of data from those sources is increasing massively. So you don't just capture database data anymore. You capture, generic stream data, right? This could be any of the stream examples that we just took. And that is essentially to build better products, to move faster in your business. So the previous, systems, either messaging systems or log collection systems, are just not sufficient anymore. And the other sort of big change that we observed coming was that, Hadoop and warehouse are just not the only destinations for your data. The various destinations are that you have probably lots and lots of specialized distributed systems, each doing something, related to that event. Like I said, you can take that event and either index it in a search system, or you can, store it in Cassandra for analytics, or you can send it to a monitoring system for alerting. It's just that the same data now needs to go to several different places. So in the absence of any sort of structured approach to capturing sort of streaming data, this is essentially what we had ended up with, point-to-point connections as new sources and new systems showed up. So in short, this was a giant mess. It was really hard to operationalize and maintain, but more importantly, we were moving very slowly as an organization. Any developer that wanted to create a new product first had to go talk to some kind of ETL team, get permission to add or change the schema, and then they would go ahead and create this data flow, which is a script to copy that data. So then we thought, the insight we had was that whether it's log files or anything else, we could actually represent this data from the source as a stream. And if we did that, and if we had a platform like Kafka, which had the ability to both ingest data at scale as well as move it in real time, then that is essentially what we were looking for, so that everything goes through one system, which is easier to manage, it is easier to scale. This is, when we were thinking about this several years ago, this is essentially what we wanted to create, which is, this concept of a streaming platform which operates at the heart of your data center. It has the ability to collect data centrally from any different place that generates that data. And because all the useful data is now available centrally, if you have a new application or if you have a new product idea, you can now just tap into this platform and get access to whatever data you need to. So, the big sort of change is, the way you move to this is sort of essentially or fundamentally move to event-centric thinking, right? Moving to event-centric thinking is actually a pretty fundamental change. So when an event happens, if you just take that event and represent the create, update, or stateful operation in your database, and then you throw the event, then you actually lose out on a lot of opportunity to use that event in many different downstream services. And that is sort of the whole idea around event sourcing or moving to an event-centric system, which is that as a response to something important that happened in your business, instead of processing it immediately and forgetting all about it, flip that sort of paradigm on its head and say, let me collect everything that happened in my business, collect it so that it will enable some downstream application in the days to come or in the time to come. And this is actually really important because, first of all, you might start with, in this example, you might start with one web app that, let's say, produces your product view events. And you have one destination, which is Hadoop. So the streaming platform in this state of the world, you might argue that it is kind of useful but mostly pointless because it's just one-to-one connection. But then you start with a web app version of things, and then you have to deploy a mobile version of your app, which essentially is the second source of creating your product view events. Now you have actually several different sources or several different locations that produce the same data. So you can see how the value of the streaming platform immediately increases. And that actually doesn't end there. You start with Hadoop, but then you realize that that data is actually pretty useful. It might be useful to send to some kind of recommendation engine, so you can either create marketing campaigns better or just show ads if that is the business model better. You will realize that you have to send it to security just so you can discount impressions that are too repetitive, or you can send it to some kind of Cassandra or Elasticsearch in order to do real-time analytics, or just process it using something like Spark. So that is essentially, the whole idea of a streaming platform. That is sort of the motivation, which is like there isn't just one source and one destination. There are just too many. So with that in mind, let's take a quick look at Apache Kafka. The idea is Kafka was built to be this streaming platform. So that is what we started with. And over time, I will walk you through how we built it in stages to be what it is today, which is more of a holistic streaming platform. So this is what we're going to go through in the remainder of the talk. So Kafka, at a very high level, it is a pub/sub messaging system. Pub/sub messaging systems have producers. These are processes that generate events. It has a cluster of brokers. For Kafka, this is where your data actually lives. It lives in the local file system, and it is fully replicated across several brokers. And then you have consumers. Consumers just subscribe to topics in Kafka, and they pull data. Now, in Kafka, subscribers are, it's a multi-subscriber system. So for the same topic, you can have several independent applications consuming the same data, and they all maintain their own offsets, and they're fully decoupled. So, the core abstraction that Kafka provides is this concept of a log. Now, a log is really an abstract data structure that has a few properties that are really important to creating a distributed commit log or a messaging system like Kafka. The first is that it is like a structured array of messages. So data is completely ordered. It is append only, and hence immutable. So once messages are appended, they never change, they're never updated. And records or messages are identified using a unique sequence number, which in Kafka is known as an offset. And this log abstraction is really what provides the ordering guarantee for Kafka and for stream processing in general. So you might think, well, this log abstraction is useful, but then how does it relate to building a pub/sub system? The way this relates is the following. When I said that you append new messages to the log, that is essentially what the producer does. As messages come in, they're appended to the log. And then a consumer, the way it subscribes and the way it gets messages from Kafka, which is something that's fundamentally different about Kafka, which is it's a pull-based consumption model. So when a consumer starts up and it has to give its offset to Kafka to say that, hey, this consumer starts consuming from message 7 onwards in order. And you could then come up with another consumer, which is a totally different application, which might say, I just want to start consuming from the tail. So it gets the latest message or the latest offset from Kafka, and it just scans forward from there on. The advantage of a pull-based model is that back pressure, the problem of back pressure is just solved by definition. Kafka is a persistent messaging system. It can buffer this data. It can buffer data which could be days or weeks or months, and I've seen people do that, which is much more than what you can buffer in memory. But then more important, this consumer is fully decoupled from the other consumer. If a consumer is slow because of several reasons, it could be just your processing or it could be a performance degradation, it does not affect any other downstream consumer. So the data storage is fully decoupled from data consumption in Kafka, and this was a very conscious and a fundamental design decision, because think about this, one consumer could be Hadoop, which might wake up and consume only several times a day, while the other consumer could be a monitoring system which needs to keep up with things in real time. So you really can't assume any property about when the consumer will be done or when it will go away. In fact, new ones can show up over time. Okay, so that was a logical view of the log. Physically, if you shard, if you want to partition that log or scale that log out, you will shard it into multiple partitions. And if you did that, then actually that is exactly the backend of the physical backend of Apache Kafka, where this log is logically a topic. A topic is, conceptually like a directory. And that topic lives in partitions which are fully replicated on a set of brokers. So as messages come in, they get appended to one of the partitions log. And we have some sort of a policy for maintaining a fixed window of the log so you don't run out of space. Either it is based on time, which is, for example, retain a week of data, or it is based on space, which is retain 1 terabyte or less per server, or it is based on a third policy called log compaction, which we will talk about later. So, time and space are probably easy to understand. So what is this log compaction and why do we have it in Kafka? So let me take a stab at explaining this log compaction concept. Now imagine that you have this table or an external database, kind of like the one we saw before. Now consider that every update made to this database, whether it was addition of a row or updating a row or deleting a row, it is expressed as a message in Kafka. Now, for those of you who are not aware, a message in Kafka has a key and a value, and a key or keyed data is actually useful for this compaction policy. Here's how. So every message has some sort of information about an update made to a row. For rows that are frequently updated, you will have several messages with the same key in this Kafka log. And for rows that are not updated, you will have just one message, right? Now, the log compaction policy is that, a couple of times what the Kafka sort of log compactor does is it scans the log and it maintains only the latest value for every unique key. So it just scans it for all the rows that were frequently updated. It just garbage collects older entries and maintains the latest one. So the impact of that is that every row that exists in your database, it also actually exists in your Kafka log. So if you wanted to recreate the content of this external database, all you have to do is you start from offset 0 in this log compacted topic, you scan ahead, and you start updating an empty database. That's how you recreate the contents of an external database. This is actually useful for a number of things downstream, but this is exactly what a log compaction policy does, which is just entirely different from a garbage collection perspective compared to the other two methods of using Kafka data. Okay, so part of the parallelism problem, which is relevant when you want to ingest lots of data, which is data parallelism, which is what we saw. How do you distribute data across machines, which is through partitions in Kafka. The second problem with respect to parallelism is actually how do you parallelize processing? So processing meaning consumption as a first step, followed by processing, which is what you do with that data. So the relevant thing in Kafka, which is with respect to consumer parallelism, is that it has this notion, or it has almost this primitive of group management. Now, group management is actually pretty interesting. It allows a group of processes, which is essentially your application, to to form a group which is expressed to Kafka, and then coordinate some action. So in terms of action, for a Kafka consumer, that action is how do you distribute the partitions of your subscribed topics evenly amongst the various instances of your consumer group, so that your application as a whole can consume lots of data without worrying about how it gets distributed. So here's an example. You have 3 partitions for this topic. Initially, you have only one consumer application process which is subscribed to this topic. So in this state of the world, the group management is pretty simple. It knows that there is only one process, and it knows that there are 3 partitions. So all those 3 partitions are assigned to that one process. Now you might want to start another instance of your application. When you start more instances of your application, your expectation is that the load for Kafka consumption is fairly load balanced. So what happens in the group management concept is the Kafka consumer library, it gets a notification from the server about a new instance showing up. And when it shows up, it coordinates its action, which is essentially reevaluating how the partitions are distributed amongst the known instances of a group. So when a second instance shows up, now one partition actually gets assigned to this second instance. The other important part about group management is that it has fault tolerance built in. So it has the ability to not just detect new consumers that showed up, it also has the ability to detect that old consumers went away. So if one of the instances of your application, let's say the new one crashed, or it was stopped on purpose, then it detects that, and this time it does the same thing, which is redistribute the partition load evenly amongst the remaining instances, which is just one instance, so that you can keep consuming data. Now, as a user, you don't have to worry about any of this. All you do is that you embed this consumer library, you subscribe to a whole bunch of partitions or topics, and Kafka consumer does the rest. So it is actually operationally very simple to consume large amounts of data. All the scale out and partitioning is fully transparent and handled by the Kafka layer. So, in short, like Kafka, we started as high throughput sort of pub sub messaging system, but it quickly sort of turned into just a modern sort of distributed platform for data streams. Here's how it's different. It has the scalability of a file system in the sense that it can handle, every Kafka server can handle hundreds of megabytes per second throughput. It can actually store many terabytes per server as long as your server has space. It actually runs on commodity hardware, so you could just run it on standard 7200 RPM SATA drives, and it works just fine. And it can do that because it actually has sequential access patterns. So this actually turns into what we say O of 1 writes, which is it leverages the capability of an operating system to cache or to recognize access patterns that are sequential, so that it's almost like you're accessing memory. The second thing is, as part of becoming a modern distributed platform, is that it actually doesn't just have the scalability, but it has the guarantees of a database. What that means is two things that are really important. One is that it has strict ordering because of the log abstraction. In fact, Kafka guarantees ordering per partition. And it is persistence. So you can store a lot more data than you can store in memory, essentially solving the back pressure problem, or in fact supporting all sorts of consumer patterns. And the last thing is that it is distributed by design. So unlike a lot of the old style messaging systems that we started, before we started Kafka, we had struggled with, it is actually distributed by design in the sense that there is a replication protocol where every message that ever gets written to Kafka is replicated across several machines. It has fault tolerance built in as a result, so even as machines fail, your data is still available. It is partitioned by default, so you can specify the number of partitions, and they get overlaid on a set of brokers. And as a result of this, it has elastic scaling capability. So you can add more machines to your cluster and move the partitions around so that you can host lots and lots of data. Since it was created, today this is roughly what the usage at LinkedIn, which is where Kafka originated, looks like. Everything in the company is represented as a real-time stream. What it amounts to is more than 1.2 trillion messages or events written to this platform per day. It has more than 3.4 trillion messages that are read per day. And the reason you have this read amplification is because LinkedIn has lots of data centers, and Kafka is actually used as a means of replicating data across those data centers. In total, that amounts to more than 1 petabyte of stream data. Today, there are thousands of engineers that use that platform. They're able to create new products every day. And there are actually tens of thousands of those producer processes that are running all across LinkedIn, across various data centers that write to all of LinkedIn's Kafka clusters. In the last 5 years, Kafka has been pretty widely adopted across the community, across pretty much the world. Right from the web companies like LinkedIn, Netflix, Uber, all the way to large enterprises like PayPal and Goldman Sachs and eBay. So back to this, stream platform idea. The next step is actually Any sort of infrastructure is as useful as the data it has. And so the question is, if you start with Kafka, that cluster is initially empty, your data is probably still sitting in various applications or systems. And in order to really make use of Kafka, you need an easy way to get data in and out of the system. And that is where connectors come in, which is the equivalent of solving the ingestion or the ETL problem on top of Kafka. So the equivalent is, think of Hadoop, and Hadoop clusters are empty. You still need to solve the ETL problem, which for Hadoop companies is likely, today it's Kafka, it used to be Flume. This is very similar except for Kafka. So in the '09 release, a couple months ago, the community released a feature called Kafka Connect. It is a framework to make it easy to both use as well as develop these connectors to ingest as well as egress data in and out of Kafka. So, why did we build Connect after so many years? What we realized is, as Kafka became more and more popular, that you needed these out-of-the-box connectors to actually get started with using the system. And as you observe every connector, it has to solve the same problems. If you want to deploy a set of copier or connector processes, then you have to worry about all these problems, which is, how do you scale your copy processes out? How do you make sure that those connector or copier processes are fault tolerant? So what if one dies, do the rest of the processes load balance and take the load for the copying to transparently continue without getting halted. For enough of these processes or connector processes, as you can see in this picture, you likely don't have just one or two connector processes. You actually, in the end state, will have several. And when you have several, it is much more convenient to have a central management system for being able to monitor how your different connections are working. And that is also a layer of problems that Kafka Connect solves. And the fourth and the most important one is schema propagation. So think about the problem of ingesting data from some sort of database, let's say a MySQL database, into Hadoop. Now, when you set up the connector to essentially copy data, it will work just fine. But a few days later, some developer would want to upgrade the schema for that table. Maybe just try imagining what happens when you add a column to your database. Usually, if you don't handle schema propagation, then what happens is all your copier processes that hope to connect and copy data from that database, or any of the other processes that hope to read data from that database, start breaking because they now expect a very different schema. So Kafka Connect, the way it solves this problem is it has schema propagation built in. So it has the ability to detect changes to schema, so that all the copier processes, as they run, they have the ability to adjust to those changes as long as they are backwards compatible. So at a high level, there are only two concepts in Kafka Connect. There are sources and there are sinks. What sources do is sources actually connect to some external thing or an external system, and they send data to Kafka. And sinks do quite the opposite. They read data from Kafka and then dump it into an external system. And both sources and sinks in Kafka Connect are streaming in nature. Kafka Connect handles all the offset management and fault tolerance guarantees, so you have the ability to deploy large-scale connections between different systems. So here are examples of some sinks or some sources that already exist today, which are supported by Confluent. The first one is a Hadoop sink, which is really popular. For Hadoop, Kafka is sort of the main choice of a pipeline to feed Hadoop clusters. What the Hadoop sink does is, it is a set of processes that runs on Connect that basically copies data into HDFS, and it has the ability to do that in an exactly once manner. And this is because of the way it is built. Now, the second sort of example is a JDBC source. This has the ability to basically connect to any database that supports the JDBC protocol and ingest data into Kafka. Now, to really appreciate the value of this JDBC source, when you have one table, You can think of deploying just one process, but it actually has the ability to allow you to add more tables or add more databases to your connector. So over time, without disturbing your data flow, you can actually add more and more things so that things get ETL'd into Kafka. And if you put two and two together, over time, across just about 5 months, the community has developed several connectors, maybe possibly more than 30 connectors to all sorts of different systems. The most popular one is Elastic. In fact, people have written 4 different connectors on Elasticsearch. And then the few upcoming ones that are Cassandra and S3 and Elastic and so on. Okay, so that was Connect. So far we've discussed sort of why streaming data, what is Apache Kafka. We've solved the ingestion problem, so data is now inside Kafka. So the next, relevant thing to talk about is stream processing. Now, this is a pretty hot topic. Companies are taking a big bet or trying to take a big bet on stream processing. And the whole notion is, the ability to process or get results faster. So I'm going to attempt to define stream processing. There are many ways of defining this term, but today I'm going to use a very specific way, which is that stream processing is, it is a paradigm for processing unbounded data sets. So for some time, it was just conflated as something that is, related to the notion of real time, but it is actually way broader than that. So before we look into more, what it isn't necessarily is something that leads to transient or approximate or lossy results. Now, for some time, some stream processing systems have been this way, but that is essentially a drawback of how those systems were designed. It is not an inherent property of the stream processing paradigm. In fact, stream processing systems, the claim I'm making is they can be made to produce or process accurate results, just like batch systems do, as well as do that efficiently. So, if you look at, paradigms for programming, I said that stream processing is a paradigm for processing unbounded data sets. So what are the other paradigms, right? There are many ways of slicing this pie, but here we're going to focus on how an application gets its input and how it produces its output. So if you look at this input-output dimension, then there are essentially 3 paradigms for programming. First is request-response systems. These are systems hopefully all of us are familiar with. In fact, they're pretty, sort of frequent in architectures, which is you send a request into the service, and then synchronously you wait for a response. And the only way to scale these services is by deploying more instances of these service. The properties of request-response systems are that they're synchronous in nature and hence sensitive to failures or any kind of performance degradation. So on the other end of the spectrum, on the far end of the spectrum, are batch systems. Here, the difference is that you send all your input in, you wait for those systems to crunch data before they send all their output back, possibly several hours later. And the main difference from the request-response paradigm is the looser coupling and the expectation around latency. So then the last one is stream processing. Here you send some input in and you get some output back. And the definition of some is totally left to the program. It could be one input or it could be n inputs. The output could be available at variable times too. Either you have one output item for every input item or one output item for every n input items, kind of like Windows. It is really a generalization of the 2 extremes, request, response, and batch. So, with respect to stream processing, something worth mentioning is that for some time, stream processing was sort of thought of as only a real-time map-reduce layer, a system or a cluster of machines that you have to deploy and understand to be able to solve these niche set of problems like machine learning or graph processing or real-time analytics. But in my experience of working at LinkedIn, creating Kafka, and actually putting these ideas in practice, we actually learned a ton of things. The first one is that the key misconception about stream processing is that it would be only used as this faster MapReduce layer. In fact, what we learned is that stream processing or the most compelling applications for stream processing actually they implement core functions inside your business and hence look like an event-driven microservice or an asynchronous application. And they look very different from just a faster version of a batch analytics job. And it has a whole bunch of applications or implications. So I'll take a quick example of a brick and mortar retailer. Here, for a retail business, there are many inputs, but there are two inputs worth paying attention to, which is sales of things and shipments of things. If you try to put this into the event-driven thinking paradigm, these two inputs for a healthy business are hopefully never-ending, so they can be represented as streams of data. And these two streams of data are actually useful for a whole set of different applications downstream. You take the streams of data, or you can send it to Hadoop or data warehouse for analytics. You might want to send it to some kind of fraud detection system. You might want to index it in a search system to power the search inventory. In addition to that, you might want to process this data more incrementally. So do things like adjust price on the fly as demands for an item changes, as well as trigger inventory adjustments. So as items sell a lot, trigger adjustments to inventory so the stores are always stocked up. So if you notice, at the top are things that fall in the what happened category. These are events that are interesting to this business. And everything else is a response to that event. This is the event-driven thinking. As a response, you might send it to a system downstream, or as a response, you might process it incrementally to produce more results. So what is this stream processing as an event-driven microservice looks like? If you think about stream processing, it is a combination of consuming data, some kind of business logic that consumes and then processes that data. Either as part of processing, you might filter things, or you might transform things, or you might join or window and aggregate things. And then you produce data back. So this is, this sort of encapsulates the entire scope of stream processing. You consume streams of events, you write your business logic, which is essentially your application, and then you produce those events back. And that is, stream processing. Now, there are essentially two ways of doing stream processing. As Kafka has become more popular over the years, I've seen that there are two different approaches to stream processing. The first one is, do-it-yourself stream processing. You take the Kafka libraries, produce and consume, and inside your application, you just do your stream processing yourself in a custom manner. If you do that, then there are some hard problems that you should know that you would have to deal with. And those hard problems are, how do you deal with partitioning and scalability? How do you, transparently scale your processing out? When you scale your processing out, what kind of semantics do you get? Do you get at least one semantics? Do you get exactly one semantics? Or do you, in fact, lose data? Then there is the whole question of state management. So some operators in stream processing, like joins or windowed aggregates, they require maintaining state. So you have to still think about the questions around state management. Then there is, the hard problem of modeling time correctly. And this is, in fact, really important in stream processing, which is the correct treatment of time. And a lot of systems, up until pretty recently, have been treating time incorrectly, which leads to incorrect results. And the last problem is around reprocessing, which is when you upgrade your application, how do you reprocess past results to reflect the updated business logic? And this is really important because, take an example of a very simple stream processor. You subscribe to streams of product view events, and you count those view events, and you update some kind of dashboard through some kind of state store. Now, tomorrow you realize that you need to filter an entire geo region out. Now, when you deploy that app, you know that your dashboard actually starts showing incorrect results for past windows because they count that geocode that you don't count anymore. And that is an inconsistent view of your application. So the whole idea of reprocessing is how do you upgrade your application as well as upgrade the data that that application kind of processes and creates. Okay, so the second approach to stream processing is using one of the many frameworks that are out there. If you're watching this space, it might start to look pretty confusing. There are several systems like Storm and Spark Streaming, Samza, more recently Flink. These are all frameworks that are essentially sort of the world they come from is the world of making a faster MapReduce layer. So as a result of that, there are some sort of implications as far as these systems are concerned. Those implications are essentially what differentiates the applications of stream processing, where when I said that stream processing is much more an event-driven microservice, that is what it means to use that as inside applications. And then there are a whole set of specialized problems like iterative processing problems, like machine learning or graph processing or any kind of SQL queries that require running long-running queries that require a cluster. Those are actually use cases that are much more suitable to these systems. And the reason is because these systems are essentially, they're developed or they look just like Hadoop does. You have a cluster, you have your stream processing logic that is expressed as a job on that cluster. There is a specific way to configure and package and deploy your job. And that, in that architecture, it's pretty heavyweight, right? You have to now deploy and manage many different machines and clusters of things that should run on top of it. Versus if you look at what an app is, it needs to be very lightweight. If you hope to do any kind of stream processing inside an app, you have your own way of configuring your app and you have your own way of packaging it, which could be Docker or Mesos or something else. So you can't really dictate a certain way of configuring, packaging, deploying code if you hope to do stream processing inside your application. So this is what Kafka Streams enables. It is a powerful but a very simple and lightweight library on top of Kafka to do stream processing. So it is a Java library today, and it has a very convenient DSL that if you're familiar with Spark, you have all the usual operations like filter and map and aggregates and joins. It supports all that, and it takes, like I mentioned, we've paid a lot of attention to the idea of time, and it has support for data flow, like windowing. By that I mean that if you're following the space, then the data flow team at Google published a paper about the correct sort of representation of time, about how to process time correctly in stream processing, and it has a whole set of implications on how to do windows correctly. And Kafka Streams conforms to those ideas. In fact, we're inspired by the data flow team at Google. Kafka Streams also has inbuilt primitives that help you solve the reprocessing problem. It is not a micro batch system, so it is a true event at a time stream processing library. So you can hope to do low latency stream processing with it. And it has the ability to maintain local state. So if you remember what I said about state, for any kind of windowed aggregates or joins, you need to maintain some state about a list of records in order to compute that operation. Kafka Streams has the ability to support local state out of the box. If you try to compare sort of various frameworks, this little graph might be somewhat useful. There are two angles at which I'm comparing things. One is simplicity, and the other is power. And if you look at the Kafka consumer, it's a lightweight library. It's pretty simple. If you remember what stream processing, it is consumer plus some logic plus producer. So the simplest thing is actually a consumer. You can consume things and you can just do lightweight stream processing on it. Kafka Streams, the way it's architected is it builds on top of all the primitives that Kafka already has. The whole concept of a log, the whole concept of a partitioned stream, the whole concept of group management and how to assign partitions evenly amongst your processing instances, those are all built in. So in terms of simplicity, it's actually just a little more complex compared to a Kafka consumer. The other reason why it's simple is it's a library, it's not a framework, so you don't have to worry about deployment at all. You can deploy a single instance of that code, or you can deploy multiple instances. It just lives within your application. Now, if you look at all these frameworks, I would put them a little bit lower on the simplicity side, just because it is a framework. It depends on HDFS for reprocessing. It has to, you have to deploy your code as a job on this framework, so they're heavyweight. Storm, which was popular up until pretty recently, that is, it has a bunch of operational problems in terms of power. All the problems around reprocessing or correct treatment of time or state management are somewhat of an afterthought, so it is a less powerful stream processing system. And Spark and Flink are actually a little more modern. They're not as simple, but at the same time they're pretty powerful. Flink particularly has sort of the same support that Kafka Streams has, which is the data flow style, windowed computing and local state and so on. So, which one do you use? If you were thinking about Kafka Streams, if you're thinking about doing stream processing inside apps, that is essentially the only thing that actually enables that is Kafka Streams. But if you're thinking of doing, iterative processing, if you're thinking of machine learning, graph processing, SQL interface to your stream processing system, then you might want to consider one of these systems, either Spark or Flink, in order to do that. So in short, like Kafka Streams is actually complementary with a lot of these other frameworks. They just are used in a totally different manner. So here is an example of what a streams application might look like. This is actually a very simple word count program. You have some kind of configuration which is mainly telling it where to connect to Kafka, because it only works on top of Kafka. You create there's a stream builder, and using that builder you ingest data, and you have all these operations, which is flat map, map, count by key, and then finally convert it to a stream. And once you convert it to a stream, you can choose to send it to another Kafka topic, or you can just write it to some other system using Kafka Connect. And then you just say start. The cool thing is that you could either run one instance of it, or you can run n instances of it. You could package it in Docker, deploy it on Mesos, or choose to deploy it on bare metal. The code that you write doesn't change. To move forward, from an execution model perspective, this is what I meant by when I said that it is fairly simple. Kafka Streams lives inside your application. So the way you use it is just like any other library. You might have a couple instances of your application. It consumes, processes, and produces data back to Kafka. When you deploy a new instance of your application, it detects the new instance. It load balances the input data evenly amongst the different instances, just like a Kafka consumer does, because it essentially just rebuilds, it essentially builds on top of those primitives. And just like a Kafka consumer, it has fault tolerance built in. So if one of your application instances dies, then it rebalances and picks up the load. So just to get this point across, there are so many deployment tools available. Essentially, that if you try to chalk this out on a coolness spectrum, there are Docker and Mesos and Kubernetes, really new and popular, and they work. And then there are sort of a little bit older systems, like Yarn was popular for some time because the Hadoop ecosystem. What I've seen is Puppet and Chef are still pretty, almost like an ops favorite still. And then you have the very old WAR files and syncing those WAR files across machines, which I'm pretty sure still happens, right? When it comes to Kafka Streams, remember I said that our goal was to make it more approachable to application developers, because we believe fundamentally that that's where a lot of the stream processing happens in a company. And with respect to that, we really cannot dictate a particular choice in terms of your deployment framework. And that is one of the key reasons why we architected that as a library, is because you should be able to use one of these different choices, or 2 years later, 10 more choices. It really shouldn't matter as far as doing stream processing at all. So in order, just to summarize a little bit, these are all the examples of key operations that you have available with Kafka streams. These are very similar to any stream processing operations that you might expect. I'm going to skip over a few sort of, key details about Kafka streams. It is mostly about internals. I wanted to, skip over to sort of the last part, which is how do you put these two together, right? So when you look at connect and streams, this is the big picture, which is that you might start with Kafka, it's empty, your data source is an external system, your sink is an external system. If you hope to do stream processing, using Kafka streams, the first step is actually to ingest data using connect. The advantage of doing that is once data is inside Kafka, it actually enables many current as well as future applications. And the other advantage is that if you were hoping to do lightweight stream processing with all the guarantees that you would like, then in order to do that using Kafka streams, data should be inside of Kafka first. So, putting all of these ideas together, this is actually what LinkedIn looks like today, which is the ability and the reality of deploying a Kafka-based streaming platform at the heart of the company. The way this works is it is the basis for a lot of the request response or microservices. Essentially, all the messaging between services happens through Kafka. A lot of the different sort of systems send data, ingest data into Kafka. Once it's available in Kafka, it actually powers a whole set of downstream applications from log search, security, analytics, monitoring. Those are all examples of stream processors at LinkedIn. And a lot of these stream processors are actually, at least some of these stream processors run on top of SAMZA, which is a system we created at LinkedIn. That is where we learned that, stream processing is not just a sort of real-time MapReduce layer, which is what SAMZA is, and that was the motivation for creating Kafka streams. And the last thing about this is that, it is also the source of truth pipeline that feeds Hadoop and the warehouse. So in some sense, it is really a source of truth streaming platform, just the way we had envisioned it would be 5 years ago. In order to put this into a sort of a familiar picture, a typical data warehouse, if you think about it in terms of a sort of hierarchy of needs for data, you have the integration problem, which is how do you store data, how do you integrate it into a warehouse. Essentially, all the ETL problems live here. Once you solve the integration problem, that means now your data is in your warehouse. That's when you actually start to think about processing your data, which in many ways is a batch ETL kind of sort of processing in when it comes to the data warehouse. And once you have processing and integration, that's when a lot of applications are enabled on top of the warehouse, whether those applications do daily reporting or alerting. At the end of the day, you have a whole bunch of these apps running that refresh a lot of important reports that tell you how your business is doing. But a stream data platform is actually not different at all. The tech stack actually remains quite the same. The set of problems remains the same. It just enables it in a totally different manner, which is the problem of integration is still there. How do you get data that originates in different corners of your company through a single platform, which is essentially the problem of streaming integration, which is why we built Kafka and Kafka Connect. The next step is really, once data is all there, then everyone wants to process it. This is where we are today, where companies and people alike are really excited about stream processing. And that is where this layer lives, which in the batch layer which in the warehouse was the batch ETL layer. It is essentially replaced by stream processing. That is where the excitement is. And pretty soon, in fact, this is happening today, but in a one-off manner, this will enable a lot of applications which are in fact reactive and real-time and process data in real time, give fresher results. And this is where we think that most of your business logic will in fact live, which is on top of this streaming platform. Apps will be built in order to get that, in order to get fresher results, or in order to end up with a much more resilient architecture. So where Confluent comes in, our goal is essentially pretty simple: to create this reality that was created at LinkedIn, almost a practical operational reality everywhere in this world. And where the product comes in is it's essentially Kafka plus everything you need in order to get started with Kafka to make this streaming platform a reality in your company. That is our focus. In practice, what it means is thinking about schema management, giving you clients in various different languages on top of Kafka, including a RESTful API, all sorts of connectors to various systems, so you can actually get started with Kafka right out of the box, along with management tools, a GUI-based sort of monitoring tool that tells you how your data is doing, how many nines you have on your Kafka data, what's the end-to-end latency, and so on. So, before I end, I wanted to leave you with a couple of resources. It's a lot of content to cover in some time, but on our company blog, we tend to write a lot. In fact, we've written mostly about all the motivation and all the nuances of the problems. There is also a O'Reilly free ebook, which is a compilation of some of Confluent blogs, and then there is you could read about the motivation and announcement blog posts about Connect and streams, which are fairly new. And that's about all I had today. Thank you very much.